Hello everyone. In this talk, I'm going to talk about resilience of time systems. This is joint work with Professor Akshay, Professor Blaise Genest, Professor Loic, Helouet, and Professor Krishna. So before going into details, let's discuss about the outline of the talk. So we start with the motivation, and then we talk about how we are modeling it, then some basic definitions, and finally the contribution of this work. So for motivation, suppose you're going from location M to V via train, and the train is supposed to maintain a timetable, go through a timetable. For example, the train should reach station M at time TM, station A at time TA, etc. Now, what happens if the train gets delayed at location B? Then it is very normal to ask, will it still be able to reach using some mechanism at station V at the time TV? So this is the basic motivation of our work, and we'll start with the modeling. So because the time is associated with this problem, time automata is a very well-studied model that captures behaviors of real-time systems. Time automata in a nutshell is a finite states coupled with real-valued variables called clocks. For example, we have depicted a small example to explain what time automata actually is. Suppose the bulb has three states. One is off state, one is on state, and one is bright state. Now, when you press the button from the off state, it goes to the on state. Now, if you press the button from the on state within 5 units of the time from the last press, then it goes to the bright state. But if you press the button after 5 units of time from the on state, then it goes off. So depending on this timed behavior of the system, there's two runs that I have depicted in this picture. Suppose the first run corresponds to the press when its button is pressed within 3.5 seconds of the first press. Then it goes to the bright state, and then if you press again, then it goes to off state. But if you see and look at the run 2, and if you press the first time, it goes to on state, but the second press comes after 6.1 time units. That's why this doesn't go into the bright state, it goes into the off state. Now, integer reset automata is another interesting subset of time automata. Why it is interesting? Because in general, time automata are not closed under complementation. That is why integer reset automata has been proposed, which is a special subclass of time automata that is shown to be closed under complementation. The definition of integer reset automata is that for every transition, the number of clocks that have been reset is empty if and only if, not non-empty, if and only if the constraint or the guards contains at least is equal to 1. That means every transition happens at an integer time, and then only you can reset the clock. So modeling. Now suppose how we are going to model this train mechanism. So in general, we have assumed two green stations where no late occurrence happens. For example, L1 and L2. So L1 corresponds to that the train has reached a station and it is have to depart the station. Departure must happen within 1 to 2 units of time. And then L2 corresponds to the train is running from in between the stations, and it has to reach the next station within 4 time units of time. Now, this rate part of the automaton corresponds to the mechanism which tries to find when the train is late, and it tries to skip a station to gain the time that has been lost due to the late behavior of the train. So, but interesting question is, so this is a mechanism that we are attaching to the system, but is this mechanism sufficient? So now let's go to some of the definitions that defines the fault model, etc. So we start with the fault model. So what is fault model? It is a map from the set of actions to a rational number. For example, suppose arrival can be delayed by 2 time units. So this we represent as a fault model, P arrival equals 2. Now, a guard of a time automaton or a constant time automaton looks something like this, where if you remember in the example, we are making sure that from a running state to the stop state, time should not take more than 4 units of time, which has been depicted as a constraint on the clock X here, but X less than equals to 4. So this can be, this is a strict upper bound is there. Now the lower bound is 0. So because it's 0, we are not showing it here explicitly. Now, because we know that the possible error that we modeled using a fault model is 2 time units, the train can be delayed by 2 time units extra than the already known upper bound. That is why we call this enlarged guard by adding the fault model to the upper bound of the constraint. Now, if we look closely, then this enlarged automaton can be partitioned into two parts. One which corresponds to good behavior, that means while the value of the x is less than equals to less than equals to 4, and another part where the value of the clock is greater than 4 and between and within 6, because I'm adding this upper bound will become 6, so this will be 6. So this particular behavior, that means when the arrival happens from greater than 4 time unit to less than equal to 6 time units, we call this behavior as faulty part of this enlarged guard. And we call these transitions that correspond, that has the faulty part of the enlarged guard, a faulty transition. Now, given the time automata, we can design an enlarged or faulty automaton AP of the train system. So if you recall, this was the upper body of this diagram or automaton was the original description of the automaton. Now, when we add the faulty part, then it goes to this state. We add this extra bullet on top of the location to represent as a faulty automatic transition has taken place, and now it can take the faulty transition to come back to its normal behavior. So now let's define something faulty. Let's define faulty and using just faulty words. A faulty word is a faulty at step I if and only if you take the prefix of the word from I1 to I minus 1, then that part corresponds to a prefix to a good word in the non-faulty automaton. But if we take the ith letter of the word into consideration, then the prefix of the word from 1 to the ith location is not a prefix of any good word corresponding to the language. Now we also define just faulty. For any faulty word, we take a prefix from 1 to I, such that I is the first occurrence of a fault. Then we call the prefix of the word W1 to I is a just faulty word. Now, given the word, when if a faulty word is being read by a run of the faulty automaton, we call the run a faulty run. And if for just faulty run, if there exists a run that reads the word, then we call the just faulty run. Now let's define what we mean by back to normal. For a faulty word of length n, it is back to normal after k steps if and only if the from after the fault to the k steps of the fault is suffix of the word in LA, where I is the faulty step. That means the fault has happened and I will give k steps. After k steps, I will expect that the behavior of the word will match to some good behavior of some other word in the language LA. So that is the definition of back to normal. Now, when we consider timed words, we will call time back to normal behaviors, and we consider untimed words, we will call untimed back to normal behaviors. Now, let's go back to our previous example. So we define two runs here, one which is a faulty run, for example, arrival at 8, that means this transition is taken at timestamp 8. So if you look closely, then you will understand that this condition is met, but not this good condition is not met, but rather a faulty condition has been met. So it goes to this state. Now then L1 decides to recover the delay by skipping one station. So it identifies that it's a late transition occurred. Now it's departures from the late station. Now it decides to skip the next station and reach to the next station. And from there it arrives at, this is skipped arrival, we name it skipped arrival at L1 in the previous state at 18 times time. Now, if we compare this word, which is a good behavior of the system, that means a run of the original automaton, then we will see that after this is a faulty transition, and after 4 steps, 1, 2, 3, 4, this suffix matches the good suffix of this good behavior. So we say that this word is a 4 BTN because of this particular run or word. Now we are now in a good position to define what we mean by resilience. For a given time automata A and a fault model P, we say the time automaton A is K for all resilience if every faulty word of the faulty automaton are BTN in K steps. That means whatever faulty run we have can come back to normal within K steps in their automaton. And we call their X resilience is every just faulty word, there exists an extension of that word such that that extension is an accepted word in the faulty automaton, and this particular word is back to normal in K steps. Let's talk about contributions. So in this contribution, we actually studied both timed and untimed resilience under the universal and existential quantifiers. Now, for general time automata, the universal resilience is undecidable. But existential resilience is X space in X space, and it's upper bounded by P space, hardness is P space. Now, we also studied the IRT or integer reset automaton example, a variant of the time automata for the resilience part, and we studied that it is X space complete for IRT, the for all resilience. But when we go for the untimed part, we see that universal resilience is X space complete and existential resilience is P space complete. Now let's study about regions and region constructions. Now, given a set of clocks, we represent nu as a valuation of the clocks, and for a given clock, v nu x represents the valuation of the clock x in the valuation b. Now, evaluation can be represented as a integral part, which is represented as the floor of the nu x, and the fractional part, which is represented as f of nu x. Now, Cx is a maximum constant appearing in a constraint of clock C. Given this, given to valuation, we define an equivalence relation if and such that if v and v prime are equivalent, if and only for all clock in x, either their integral parts are same or both of the valuation is greater than the maximum constraint of the clocks, or if both integral values are less than the maximum constraint, then their order of the fractional part must satisfy on both of the valuations. And if their valuation, if any clock's valuation is 0 in one valuation, then the other clock's value, in other valuation, the same clock value must be 0. Now, this is the equivalence relation, easy to check. And the regions are defined as equivalence classes of this relation. Now, given this, it has been shown that one can build a region automaton on the called RA of the given automaton A, and the automaton recognizes the language, untimed language of LA. A time automata is not an untimed resilience. Now let's go to the untimed resilience property. A time automata A is not untimed for all resilient if and only if there is a faulty run that is not untimed BTM. What does it mean? So if you look back to the definition of for all resilience asks that if every faulty run comes back to normal or not. So if we can show that there exists at least one run that doesn't comes back to normal, then we can say that the automaton is not for all resilience. So because we are dealing with the untimed part, it is sufficient to take the region automata. So we start with the constructed product automata using the box cross K. The state space of the product automata is the locations of the faulty automaton, and it also keeps the regions or reachable regions, all reachable regions are the region automata, and it also keeps a counter. Now it progresses normally till a fault happens, and then it goes till k steps, and from there it tries to mimic. For example, if L automaton AP sees an action A, then I will see can there exist any state of this current subset of the region automata, state of the region automata, that reading A we can progress in the future. Now, if it happens that there exists a faulty run for which we reach a state where this becomes empty, this state because then that means we cannot progress anymore. That means that there exists a run of this automaton which cannot get back to normal in the untimed sense, because this we cannot progress anymore in the region automata. So this gives us a easy result of an exponential, because we know the region automata is already exponential state, and now we are doing doubly exponential of the size. Now we can enumerate all the states of this doubly exponential space in X space. So that is why this problem is in X space. Now the hardness comes from the untimed language inclusion of time automata. It has been shown that the untimed language inclusion property of time automata is in X space, is X space complete. Now let's read this defined untimed exit resilience is P space complete. Now we have to show that if we reach a just after a just faulty world, can we reach for all just faulty work, can we there is does there exist a extension of just faulty work which is back to normal? That is what the definition of existential is. So now suppose that Q is a state of the region automata, faulty automata, that reached after just faulty run. Now, one can non-deterministically guess in P space because the state space of the region automata RA is exponential. So we can non-deterministically guess in P space that there exists an accepting run with the same suffix as an accepting run of the Q after K steps. Now, after this guessing, we can check that the run is possible from that run is in P space. So this problem is in, so we can solve the time existential resilience in P space. Now the hardness comes from the emptiness problem of time automata. So we have shown that we can reduce the emptiness problem of time automata to the untimed existential resilience of time automata. Now let's go to the domain of time resilience. So time resilience, as we mentioned in our result table, that it is in general much difficult than untimed resilience. So why is the case? The first immediate observation is that the number of just faulty runs is infinite. Because we are also dealing with the timestamps of the event that occur during the runs, and the events, the timestamps are all real. So it is possible that it is obvious that there will be infinite possible just faulty runs of a given time automata. Now the second observation is that in time resilience, we need to ensure that the suffix happens is the same time and the same event happens. But to guarantee that the events happen in the same time, we need exact timings. But when we use region automata, we don't deal with exact timings. We do an abstraction of the valuation. And this is a problem that we face while solving time resilience. So let's start our observation or study of the time resilience with an undecidability result. So now we have proven where we have able to reduce the problem of language inclusion of time automata, which is known to be undecidable, to a problem of forward resilience problem. For example, we have developed this gadget. Now, when we feed this S1 location with the time automaton LA, the time automaton A1, and S2 with the time automaton A2, then it is not very difficult to see that if we solve this whole automaton, including the A1 and A2 and the gadget, that if we solve the forward resilience with 2 steps for this automaton, then we will be able to show that LA is subsumed, it is a like language inclusion problem of LA, A1 and A2. We will be able to solve that problem. Now, this was so far easy, but let's go to existential resilience. Now we have a result that existential resilience is in X space. So let us define the product automaton AP times circle times KA with the following state space. So the idea is that the transitions will synchronize time till K steps of the fault, because we don't care what actions happen. We have to make sure that after K steps after the fault, the both events and time occurs same time both of the automaton. That is the definition of existential resilience. So in the product automaton, what we do, we make sure the transition synchronize in time, not actions, till K steps of the after the fault. Then after that, it have to synchronize on the actions and time both. Now it is accepted, so in both LA, AP and APR falls into the final state of the respective automaton. Note that this is a timed automaton. This is product of the time automaton. It's not region automata yet. Now it is basic intuition that we will apply region automata on this automaton and it will get solved. But we will see later that it's not easy or it's possible using just region. So let's keep in mind. So for example, when we have a run row of time of this product automaton, then this run will have two components. One component corresponds to a run of the faulty automaton. Another component will have a run of the non-faulty automaton. Now we say that this run of this product automaton, the first component corresponds to the run of the faulty automaton, and the second component corresponds to the run of the non-faulty automaton. Now it is easy to check by the definition of the product that if a faulty accepting run is back to normal in K steps, then there is an accepting run row of this product automaton such that the projection on the first component that I mentioned earlier, because this corresponds, there are two components of this run. One is a run of the faulty automaton and the one run is non-faulty automaton. And suppose the faulty automaton counterpart of this run is a row F1 and is accepting. That means there exists a run, because this the way the product is defined, till k steps of the fault, it synchronizes time, and then after a k steps, it synchronizes on both an action and reaches an accepting state of the both state. That means this row F, and if we say the first component is in row F, then obviously row F is in BTN. Now we have to show that for a given just faulty run row F, there are infinitely many runs of this because of the different timings, because of infinitely many row I runs of the A possible that we can product with each and get this one so that it reaches a particular run, right? So there are infinitely many such runs possible. So how to deal with this infinity? Now, as we mentioned earlier, it is intuitive that we use region construction. But when you use region construction, that guarantee that it reaches a particular point, or rather synchronizes on time and action after case of the fault, is not going to be true, because region construction only keeps the clock's valuation information inside it. It just keeps the region information, not the exact timing information, timestamp information. So then what do we do? So we improvise a region automata. We called it strong region automata. What we do, we add a dummy virtual clock x iota such that it resets in every global time, and add a constraint to each transitions x iota less than 1, and a virtual self loop to each location with guard equals to 1, and immediately that transition also resets the clock x iota. So this simple manipulation allow us to incorporate the global timing information or global time regions into the clock regions, because now this clock is being reset in every global timestamp, and it makes sure that the timing information of the timestamp information or regions of the timestamps are also part of the time region. It is easy to check that even though we are adding extra clock, the language accepted by the automata remains the same. So what difference does it make? So let's take an example. Suppose this is a simple automaton, and row 1 and row 2 are two runs of the automaton that goes to the same region, same runs of the region automaton. But if we look the timestamp of these events, then we will look at that this D2, the fractional part of the D2 is less than the fractional part of D3. But if we compare the same with the second run, the fractional part of the D2 prime is greater than the fractional part of the D3 prime, which is not correct. Which is not what we want. That means that even though they go through the same regions of the clocks, it doesn't go through the same region of the timestamp of the events, which we really need to solve the resilience problem. But if we apply the strong region construction, for example, that we add this extra clock x iota, and then add a self loop that resets this x iota on every time it reaches 1 timestamps, and we add the extra constraint that x I is less than 1 on every transition, then if we construct the region automata, then we will see that the strong, we call it the region automata, strong region automata of the automaton A, then we'll see the previous two runs correspond to two different runs of the strong region automata. That means this extra clock, we're able to distinguish between the two runs of the automata. Now, given this results in hand, we will try to see how we have used this information to prove that existential resilience in X space. So we first define a T, set T. The T corresponds to a set of states of the product automaton that is reachable following a faulty run of row F. So this represents, suppose row F is the faulty run, and row F times represent a product, is a run of the faulty automaton, a product automaton, such that the first component of this run is row F. Now, if we see the strong region construction, then we will be able to see that this S is a region abstraction of this set P. That means that we will take what are the regions that being reached in the strong region automata correspond to this state into this state. So for example, suppose this state represents this product automaton, and this state represents the state of the strong region automata corresponds to this state in the normal automata. So now we will show that how this state has been constructed. Suppose this is a faulty run in the origin automata. Now row prime and row prime, two different runs of the original or non-faulty automata. Now when we do a product, it is possible that they follow to the same region. And then even though they reach some different state of the normal automaton, they reach the same region and the same count. So this is how we compute the state S. Now let's define something that we call safeness. Safeness of a state S that we defined previously, if we can reach an accepting state of the region automata from any state inside this state or the safe state. Now let's go back. So now what we show, previously we have shown that rho 1 and rho 2 are two faulty runs, and S1, if these are the two sets of the S that we have computed previously, and if rho 1 and rho 2 both goes to the same path of the strong region automata, that we are able to show by retiming that these two sets will be same. Then it is sufficient to enumerate all possible sets S such that rho is a faulty in X space, which is possible in X space. And then checking if any one of the such states is a safe state is possible in P space. So we are able to solve the existential resilience that is in X space. But we have shown hardness of the P space by reduction from the emptiness of time automata. So what is the future work? So we start with continuous resilience. So instead of counting the number of steps that we go, we consider the exact time elapsed after the fault, and that we call continuous resilience. The resilience of subclasses of time automata. So we have studied resilience under a subclass called IRTA, or integer reset time automata. So there are other subclasses that are possible, which are quite interesting to see how the resilience is being observed there. And the resilience of a more complicated system is recursion randomness. Right now, we are only studying resilience of time systems, but this opens a new window to study resilience under more complicated systems like time push-down automata, time multi-stack push-down automata, etc. Thank you, and I'm glad to take any questions. And these are the bibliography. Thanks.